I'm going to go talk about micro and nanorobots, which is this small scale tiny devices. People sometimes confuse them with weapons, but I will show you that are not weapons actually. But Andres asked me to talk about myself before, and so I'm from this. I consider myself from this tiny town that is 20 kilometers north east from Barcelona. It's called El Masnou. It's in the seaside. It's a very beautiful place, not very touristic, at least at the moment, and I'm very grateful to that.
This presentation.
I'm a chemist by training. I studied at the University of Barcelona, and I put this image of this from this Disney movie, Basil of Baker Street, the great mouse detective, because I decided to study chemistry after watching this movie, because he was discovering using chemistry tools where the Villain Ratigan was hidden. Then during my PhD, I decided to visit Switzerland, because I found out that one of the researchers that were working in a similar topic I was moved to Switzerland, working in this fascinating world of micro nanorobots. So I applied a grant from the Catalan government as a visiting PhD. So I landed at ETH Zurich. Yeah, and I've been since there almost 16 years, a little bit more than 16 years, where I could develop my career on this area of micro nanorobots. And well, if you're not very interested in my science, perhaps you're interested in my humanistic side. I am also a composer in my free time. I compose music. If you want to hear me in YouTube, you have here this code, and you can search for me. And I usually compose music for poems. So and I will get this book of poetry done by me. It will be appear soon in a month. It will be published and released. It's in Catalan. Maybe somebody tries to translate it into English. But okay, enough of myself. I'm going to talk about micro nanorobots, and I think I will start by stating something that is quite obvious. We live in a world increasingly surrounded by robots. We see robots in hospitals, in operating theaters, like the Da Vinci surgical robot, but there's a lot also of development on robots at in different areas. We see robots that are designed to mimic the complex motion mechanisms of organisms, like this swimming snake or this animal, this quadruped that is actually developed at ETH Zurich. These robots are designed to reach difficult places that for us, okay, and to jump obstacles. And talking about places difficult to reach for us, there is also robotic rovers like this one designed by NASA to inspect the Mars planet. We also see a lot of development on reconfigurable robots that are modular and they can change their shapes to accomplish their tasks. Robotics is also in manufacturing, in 3D printing. Okay, who doesn't know drones that can do these amazing choreographies? I don't know if you have seen these choreographies of the New Year in Beijing. But this is amazing. Soon the theaters will be filled with drones making a ballet. Of course, there is a lot of research on humanoids and design to accomplish difficult tasks for us or helping us at home. And of course, some of us, we have this tiny robot called Roomba that helps us to keep our homes free of dust. No? And as soon as we are going down in the scale, we find these little cousins from these big robots we call the micro nanorobots. And one of the most sought applications for these small-scale robots is in the biomedical area, which in the near future, and I hope I can convince you about this today, we will see these devices then realizing drug delivery to confined spaces, diagnosis, and sensing, and so on. But is this an idea of the 21st century, these micro and nano devices? Indeed, not. In the 60s, already Richard Feynman, the famous physicist and Nobel laureate, in a talk, stole the idea from one of his friends and quoted Gibbs and said, "Why don't we swallow the surgeon?" referring to the idea that one could implant in our body a device and help addressing a medical condition. And in the same year, same decade, in the 60s, we saw the release of this movie, The Fantastic Voyage, okay, in which we saw the miniaturization of a small boat, okay, with scientists, and they were injected in the body of an injured scientist with a brain injury. The mission was to save his life, okay? Unfortunately, today I will not show you how to miniaturize people, but maybe in the near future I can show you that. Nevertheless, in the 90s, we saw also the publication of this controversial book by Eric Drexler, Genes of Creation, where he imagined a world in which we would engine DNA machines to address medical conditions. And I think we are not far from this, okay? We see a lot of genetic development and biotechnology that is pointing to that. But if this idea is from the 60s, how comes we didn't hear from micro nanorobots until recently? And because there were a lot of challenges to solve. And one of the challenges was materials. But now we can control matter in unprecedented ways. And I'm going to give you an example. For instance, helices, helical structures. Okay, I think as architects, some of you are very interested in this geometry. But this is a geometry that is common in nature too, as you will see later. But coming back to what I was saying, to fabricate a helix, now we can fabricate micro nanohelix of different materials with different fabrication techniques. We control chemistry in many ways, so we can take these tiny helices and put these little crystals here, okay, that are porous materials, and we can encapsulate drugs. And we can take these structures and make them controllably move in a fluid. And another challenge we have to face is, okay, we have these tiny structures. Can I put a battery or a motor in a micro or nanostructure to make it move? So here you see one of the smallest batteries made until today, okay? It's not even 1/10 of a dime, but you can take this battery and put it in a nanostructure or a microstructure to propel it, okay? So those are the two grand challenges, or in my opinion, that were impeding the development of micro and nanorobotics in the past. And what the community of micro nanoroboticists have been doing in the last decade, what was it? Trying to understand how to impart locomotion to micro nanostructures. And I'm going to go quick through this slide, which is not very complicated. But so when we have a small object swimming in a fluid, we have basically two forces: inertial forces, forces related to weight, and viscous forces, forces related to viscosity. And the ratio between these two forces is this number, the Reynolds number. And here you see in the denominator the viscosity. This means that when my device is very tiny, L is the characteristic length of the device, viscosity dominates, and this has consequences in the way we should move in the micro nanoscale, or basically how to move micro nanostructures in the nanoscale. I don't know if you have tried to move in honey, but I will anticipate that for us, moving in honey is the same for a bacteria moving in water. So what I meant by the consequences, and we come back to a funny name for a theorem, the scallop theorem. The scallop theorem was coined by Purcell. Purcell was a Nobel laureate physicist. And this scallop theorem, what it states is that we cannot get net displacement if we realize a symmetric motion with time, like what the scallop does to move, when we are in low Reynolds number regimes. In other words, in highly viscous media, we cannot use this symmetric motion to be able to move through fluids. And he has a beautiful talk called Life at Low Reynolds Number, in which he shows how a swimmer should be able to displace. And he proposes this swimmer, which is a 3 links with 2 hinges, and he proposes these 2 sequences. And if you check out these sequences immediately, you will realize that in sequence A, in D, we are breaking the symmetry of the motion in time. This means that in sequence A, we will get net translation. And in B, no, we will not be able to move. And this has been demonstrated also mathematically and so on. But in the same talk, Purcell watches at nature. Nature always gives us lessons. And there are microorganisms and cells that are able to move at these low Reynolds number regimes in high viscosity media, right? And he identifies basically two main mechanisms: rotating a chiral arm like a helix, or waving an elastic arm. And let's watch at nature. How a sperm moves in highly viscous seminal fluid? By waving the flagella. And it creates a traveling wave which allows to move through the seminal fluid. Also, bacteria like E. coli, they have a bundle of helical flagella which they rotate, and they create this kind of corkscrew motion. Corkscrew motion is what you usually try. You always use this mechanism on Friday evening if you drink wine. So if you take a bottle of wine and you try to open the cork, you will do a corkscrew mechanism, because if you try to push it and don't rotate it, you won't be able to go through the cork. So bacteria to move through water is the same mechanism, right? And there are other mechanisms. For instance, here, what you see is a neutrophil. Neutrophil is one cell that belongs to our defense system. And neutrophil has a mechanism, a physicochemical mechanism that allows him to move by friction against the flow in our blood vessels. So we learn a lot from nature, and researchers, what they have been doing during these last 20 years, last 2 decades, is trying to design devices that they can move at micro nanoscale. Some people, for instance, like to use chemical reactions. Here, what you see is very tiny nanostructures that they are catalysts. Catalysts are materials that accelerate chemical reactions. So they are dropped in a solution containing a chemical, and because they are catalysts, they accelerate the decomposition of this chemical. And as a result of these chemical reactions happening around, you can get motion. As you can see, using this approach, you don't have a controllable way of moving these structures, right? Another approach, and this is what we use in our lab, is using magnetic fields. And here you see tiny nanowires. You can see the scale. They're very tiny, 5 micrometers. But you can already identify the richness of using magnetic fields to manipulate, because what you see here is the same nanowire, but the only thing we do is vary the rotation frequency of the magnetic field. And you can obtain 3 different mechanisms, right? Like tumbling, precession, and rolling motion. Rolling, like the neutrophil cell. You can also use light. So here you see micrometer structures. They are photocatalysts, which means that they are catalysts that are activated by light. You drop them in a chemical solution, you shine light to them, reactions are happening. And the interesting thing you can see is that depending on which light I apply, I can control the speed of these structures. So I have a more controllable way to manipulate, okay? And other researchers, what they do is, okay, the nature offers me a wealth of microorganisms that move. So you can engineer E. coli bacteria to be attached to a red blood cell and push it, like in this way. What do we do in our lab is use magnetic fields. Why do we like magnetic fields? Who has never played with magnets, okay, as a kid? But no, it's not the reason. The reason is that magnetic fields are already used in hospitals, in MRI. They are biocompatible in a wide range of conditions. And they allow a lot of different things, as you will see now. But perhaps at this point, you might ask, okay, this is not, when I see these structures moving, this is not my idea of what a robot is, okay? And I always like to show this analogy. So this is a robotic arm, okay? Perhaps you have seen a robotic arm in a 3D printer or in an assembly chain in a car assembly chain, okay? So basically, in a robotic arm, you have an end effector, okay, that will do the task. But to move this end effector, you have the joints, okay? And the joints, so as an input, I have the velocities of these joints. And as an output, I have the end effector motion. And basically is what the end effectors will realize ultimately one task: grasping, moving an object from one side to another, shaking, whatever. So when we use magnetic fields, basically it's the same. We have unit, which is an electromagnet, that by circulating current, you generate a magnetic field. Okay, this is our input. And our end effector is a magnetic structure that could realize similar tasks as this terminal on the left. And that's the robotic part of our systems. Okay. I don't want to go into more details and forget about these equations here, but as I have said, you have played with magnets when you were kids. So if you take a magnet, and you approach it to some nails, they will come to you. Okay, they will feel a force. Okay, and if you rotate the magnet, also the nails will rotate, right? Because they have an easy magnetization direction. So if you think about these mechanisms, you can design different micro nanostructures and respond differently to these magnetic inputs. You can go simple. You can take a pillar, magnetic pillar, micro pillar, and move it with gradients, magnetic field gradients. As let's say, the analogy here is I have a magnet and I move it around. Okay, it's a bit more complicated than this, but just to simplify. But okay, if I know very well the properties of this pillar and the forces that I am exerting on it, I can understand forces at micro nanoscale. For instance, I could understand the forces that a cell is making to swallow, to engulf one of these structures. And you might ask why this is important. Okay, we are designing micro nanocarriers for drug delivery. I want to understand what are the interactions with cells. We can also achieve the motion of cells artificially. So here what we design is a nanowire with two magnetic heads, two little hinges of polymer, and a long tail, okay, of a polymeric tail. And by applying an oscillating magnetic field, we can mimic very well the movement of an eukaryotic type cell like a sperm. And we can move in highly viscous fluids. We can also mimic the bacteria by creating this artificial helical flagella. This is actually one of the pioneer experiments that Professor Brad Nelson, who is director of the lab, one of his pioneering works. And so basically here what you have is a rotating magnetic field. You rotate the head, and by rotating, you create this corkscrew locomotion. As I said, how you open a bottle of wine is the same. And of course, we can design structures that also roll and mimic the neutrophile. And here you can see is one of these nanowires manipulating a very tiny bead. Okay, you can see the scale, 5 microns. This bead could be a crystal of protein, it could be a cell, so a delicate object that you don't want to destroy using your hands, right? We can also create structures that are adaptable, and adaptability is crucial in nature. To survive, to get your prey, to be successful, you need to adapt. Okay, and this is what this parasite is. It's very successful in infecting. This parasite, maybe you know, it's Trypanosoma brucei. Okay, it's transfected by the tsetse fly, and it's causing the disease of sleep disease. And the success of this parasite is that it can change its shape depending on where it is, depending in which tissue it is. Either is the tissue of the fly or our tissue, and that's why it can go from the fly to us and even cross the blood-brain barrier. Some people are crazy designing the structures to penetrate drugs to the blood-brain barrier. But this tiny organism from nature can do it very successfully by changing the shape. And what did we do is try to mimic the shape reconfiguration of this Trypanosoma brucei by creating these micro robots that you can see that is swimming with magnetic fields. Now I'm going to put the same device in a hot water, and you will see that it opens. So it can adapt to temperature changes. And I could use this feature to open and release cargo, like for instance, drug. And of course, we are engineers, we are chemists, and we like to play with our imagination, and we can create very complicated structures, right? For instance, we can create this 5-leg spider and move it around. We can create these tiny vehicles and move it. We can make these structures to float on water. by playing with the polymers that we use, or we can make them sing at the bottom of a reservoir and roll. Okay, and this is very beautiful. But but you might ask yourself the question now: how we do translate this into the operating theater? So here I have a list of challenges or aspects that one has to consider to be able to do that, right? One is, some of course are which magnetic materials I can put in the body, how much therapeutic cargo I can load, the biodegradability and biocompatibility of these robots, which contrastations I want to track these robots in the body, right? I want to make them adaptable or multifunctional. I want to control many of them at the same time. Can I have enough, the machines that are in the hospitals for imaging and tracking are ready to track such tiny structures? And finally, do we have magnetic navigation systems that are suitable to operate in a healthcare environment? So there are many questions to address. Today, I'm going to talk about one, which is multifunctionality. And as here is a parametric academy, multifunctionality means that I will have to play with a lot of parameters, right? So one of the nice things from magnetic fields is that they enable multiple tasks. So I can just drop a magnetic structure in the bloodstream, and with the magnetic field, I can play like the steering wheel, right? I guide it. Okay, now turn here. Okay, turn to this vessel. I love that, that would be so easy. Then I can also achieve active motion, right? So you have seen different ways in which I play with the geometry and the magnetic input, and I have rolling motion, corkscrew motion, and so on. But there are other things. There are magnetic materials that they deform when you apply a magnetic field. Or the heat. I could use the heating capability to ablate the tissue, to burn a tissue like a cancer tissue, okay? But the very interesting thing you can do with magnetic fields is delivering electricity. And how do we do that? Well, there is a way. There is these materials that when you apply magnetic fields, they change the volume. And then there is these other materials, which are magnetostricting materials, by the way. And then there is these other materials on the right, piezoelectric materials, that when they get deformed, they generate an electric voltage. Okay, if I couple these two materials, okay, and I apply a magnetic field, and if they are really in an intimate couple, what I will manage is when I apply the magnetic field and the magnetostrictive becomes fat, the stress will be transferred to the piezoelectric material, and I will generate an electric charge. And you might ask your question, for what do you want this? Let's go back 200 years ago. And I'm going to show you a scene of one of my favorite movies. I'm a bit romantic. I like 18th century. Unfortunately, we cannot wear the wigs now, but it's okay. So the electricity and the spirit is the same thing, is what the Marquis of Bellegarde, an illustrated man, is telling to the engineer Baron Ponce de Don de Malawa. And this is a movie that takes place in the pre-revolutionary French. This engineer lives in a region of France. La Dome is affected by mosquitoes, because there are a lot of floods, and mosquitoes bring diseases. And he needs to build dams to contain the floods, but he doesn't have money. And in that moment, there was no European Commission, so he had to ask the king for that. So he goes to the king and tries to reach him, and he realizes there that to get the favor of the king, it needs to play the court game, what we would call today the political game, but in a different manner. But he meets this wonderful person there who helps him and shows him experiments. He's an illustrated man. And indeed, these visionary scientists from the 18th century were right. Electricity and life are connected. The membrane of cells have a difference of voltage, which regulates different processes like metabolic process. Neurons communicate by electricity. Our bones, when they are fractured, they have collagen fibers that when they get stress, they get electrically polarized and they help in regenerating the bone. There are bacteria that use this cable to transfer electrons and to nourish from these electrons. Spiders using electrostatic charges to be able to fly. or there is even animals that use electricity to catch their prey, right? And for what we can use electricity for biomedicine, to stimulate cells in different ways. We can induce their death. We can differentiate them. We can take stem cells and transform them in neurons. We can help drugs to be inserted in tissues. But nowadays, how electrical stimulation is done with electrodes that, although they are miniaturized, they are still invasive, and they cause a lot of problems still. You need wires, you need complex miniaturization processes, and so on. So what do we do today is, in our group, is design very tiny materials that can deliver these electric fields, as I showed before. And we did one of the first micro robots that deliver both cells and magnetoelectric nanoparticles, right? And we culture them with cells, they degrade, they spread these magnetoelectric nanoparticles, we apply magnetic fields, and we are able to neuronal stem cells to differentiate. And you can see here the neurite connections. And this is one of the latest experiments we have. This is a 6-micron micro robot made of cells and magnetoelectric nanoparticles moving through a very tiny vessel of an animal. And I'm reaching the end of my talk because you have seen a lot of things that we are doing, and but one of the questions we have is, okay, we have the perfect micro robot, and now how we design a medical procedure for that? Does it make sense that I inject a micro robot here to be able to reach the neck? So how do we implant the small scale devices and where? And then how do we navigate? And what are the advantages for the medical doctors to use these devices, right? These are the questions that we have to ask ourselves. So if I inject a micro robot here, unless it's super fast, for the micro robot to go from this point to this point would be like for us to go on foot from here to Barcelona. So this is not viable. Unless we leave it to go with the bloodstream, okay? That's another option, which we also contemplate. But in our group, we also design the tools that allow the implantation of these devices and navigate these devices. This is one of the latest systems that are being developed by one of our startups, the NanoFlex startup. They are here close in the PAZ Institute. And then they design special catheters that can, for instance, modify their stiffness when they go through the vasculature. Here you see one of these catheters going through the vasculature, and when it's changing the vessel, we can change the rigidity state to be able to move. Then now we make it rigid to continue and to avoid buckling of the catheter. We also design catheters that have mechanisms to inject the structures. This is also important. This is a model of a spinal cord, and you can see how we inject thousands of nanorobotic structures here. And we have a long story on navigation systems. This is more the work from Professor Nelson, with whom I worked since I came here in Zurich. And when I came here in Zurich, what I had to do is this tiny micro robot that you see here injected in this eye of a rabbit. And we did the manipulation experiments of this. We use rabbits because it's the best model for ophthalmology. So if it works with rabbits, it works with humans. I have to tell you that the rabbit didn't suffer because the needle we use is 13 gauge, which means that you don't need to suture this. So we can inject the micro robot without, in a sutureless manner, okay? There were several designs. This was a design that was realized by one startup, and we could do cardiac ablation with this system, even with large animals and humans. But as you can see, this system here, it's quite bulky, okay? And not all healthcare facilities would take it in. So what we did is to make a smaller version of this. And we are currently testing our micro robots with this system. This is a catheter. So the nice thing from this is that the doctor could be let's say, here and operate in Botswana, because I can manipulate this. And the advantage of using the navigation systems is not only the precision, it's that avoids the practitioner to be exposed constantly to X-rays. Okay. And this is one of our latest experiments in manipulating a catheter in the facial artery of a pig. And soon, in January, we have planned to use these catheters to deploy micro robots and test their trackability and steerability in a vascular system of a large animal. I think I talk enough. Of course, I wouldn't be here without all these people and many more, and all these funding schemes and collaborations. And I am stealing a quote from Arthur Clegg. I'm sorry, it's in Catalan, but what it says is, any technology, any advanced technology is indistinguishable from magic. Thank you very much.
Thanks a lot, Salvador. I don't know if our guys have a question, a lot of them, or ideas, discussion.
Do we get questions online or only?
I think we have some students. I will check if they are asking, and if not, we will start. I mean, I think it's really fascinating not to see all this work behind, no? All these years of work behind, and also to obtain the service system that they are able to move, to change, and also to be painless as much as we can with technology. And I want to ask you, when you think we will start to see this technology like something normal, let's say, apply for maybe animals first and humans?
So we are currently starting with animals now. It is not very easy, but I think I was commenting to you this before. Doing it with animals is not just to test that your therapy is going to work. Is also, you also have to start this as soon as possible, because you realize about details or aspects from really doing these experiments that you don't foresee when you're in the lab. And like you are in an operating theater, how much voltage I have to connect the system, or is the floor properly reinforced to have a large system, or a procedure for sterilization, and so on. So and it is also very important to have a dialogue with doctors before, because they would tell you, oh, this would work, this wouldn't work. When you are in the lab, you have a lot of imagination and you are in your world, but I'm not saying that it's not the real world, but hospital environment is a different story. So that's why we are now working with large animals, and hopefully maybe in 10 years we find one application or two in which micro robots can be used to treat certain diseases. We are currently now exploring this. Till now, we have been understanding some scientific fundamentals or aspects of cytotoxicity and so on. But until you don't try with large models, it's difficult.
Suppose you need to have a lot of tests and try in years that we 100.
For instance, you could design a very beautiful catheter for a rat. This is very challenging to design a catheter for a rat. But then why to put so much effort if later I need a catheter that is larger for a human, right? Maybe it's useful because maybe you have to treat a kid and the dimensions of certain parts. You never know, but you have to push everything as you can, as much as you can.
We have any question for the public?
For me, it's like interesting because how many you are in the team, and if they are different kind of disciplines, or
so we are a lot of people. We have a lot of engineers, electrical engineers, mechanical engineers, material scientists, chemists, biologists. So we have a very diverse multidisciplinary team. Yeah.
the architects. Architects are relevant with architects.
Well, I find architecture, I think it could have a lot of I think there is a lot of material scientists that can contribute. There is a lot of inspiration, could be a lot of inspiration from biology and nature. Gaudí is an example of nature inspiration, I would say. And I think a lot of smart adaptable systems, they could be implemented in many parts of a building, right? There is people working on smart materials that react with light, and then you can use these materials to cool down the building, or to avoid overheating of the building. So
I think I'm really enthusiastic. I'm waiting for the video, also auto repairing.
Auto repairing.
yes, there is a lot of work on self-healing with polymers and yeah.
For us, the materiality, that's how nanotechnology can change also materiality.
Mm-hmm.
It's true that will take a lot of years to make bigger the scale.
Indeed, I saw a paper long time ago, which this structure that I show you that mimics the sperm, it proposed to use a composite of this structure because as it is flexible in one part and rigid, the composite will have very cool properties for mechanics. I don't remember now what exactly was it, but
this is the connection.
The problem is sometimes how you scale up the fabrication of this. It is not easy, because now we are working on a lot on magnetic nanostructures, and we realize that when we want to produce them in big batches, we have troubles. So
thanks a lot, Salvador, for opening our brains, and also this really nice lecture. I think it was really fascinating, all the work behind, also about geometry, chemistry, physics, everything together. And I think will make us to continue thinking during next day, and maybe write you and to listen your music for sure. Yeah. And your book that is also coming.
If you don't like, forgive me.
No, thanks a lot for your knowledge and coming here to share PAZ Central. We will close the connection and we will start with the apero. I don't know how much time we have, but we will start with some drinks.